fast. Once you work with LaTeX and you write your code, all you do is you have your predefined commands.
I did something similar in Python to take a bunch of images and make a document.
I did that in
To make a
HTML
PDF.
once.
No, Word document.
Oh,
I
Hey, Sam,
you
how
can
are
do
you?
it in PDF as well. Oh, hey Sam, did you know about Young Investigator?
I saw your email, but
It's today. I was just lazy when I was in bed when I was like, oh, I should email him.
the Young Investigator works today.
No, the due date is today for
ACS.
so it's for ACS. And yesterday, Christine said that they have less applicants than they have awards.
So you're going?
I did not apply to ACS. I
Are
cannot
you
go. He didn't go to ACS.
Are you going to ACS?
So
He may go, but he doesn't know about it.
Oh, maybe coerced into it.
so
You should do the Young Investigators Award.
I don't know when it
So
is.
free $250 because they have fewer applicants than awards.
Unless they put out the word and now there's not. But if you're interested, I would go talk to Seth.
Rasmussen.
Because I know the guy's email that I talked
But
to
it's fun.
last
It's
year,
good. It's
but
an opportunity to present your research too.
Okay.
To,
and it's
small-
like I think like 10, 15 minute
relatively casuals, I think.
like
Yeah, it's just we.
I will just bring everything up.
last year it was like everyone
I will announce
presented
when
was
we need
there
to
and then the
We
three
thought about it.
like ACS members.
Well, I think
that
the
were
emails
judging.
only go to members of the Red River Valley chapter, right?
Yeah.
So
So,
and Seth's office is
are you an
across
ACS
the
member? Yeah.
hall.
Know where he's at.
Yeah, I should probably
Do
get
you know
on
who
that.
is judge this year? I got
Going
an
to
email
ACS,
for
yes.
judging. They're looking for judge.
I don't know,
It's the
Well,
same as
yes.
last year.
but
I don't know.
like it's pretty good.
Which organization did you
It's a
talk
travel
to?
grant for the San Francisco meeting.
Yeah.
So I was-
So like if you win, I think you get 50 or something, which is
The bar?
pretty good.
Did I answer that?
But I don't know if your boss is.
First prize
I
is
think
$500.
that's the answer to that
right?
question.
I don't know. I don't know.
First prize is $500.
They have some money that you can get. The only thing is, I believe it is in
But that $8 bill was a bar.
Mayville. So we had to drive to Mayville
Just
one
kidding.
Saturday.
You're from Wisconsin.
Postdoc is
Yeah,
to present my presentation to them.
When
So-
did that go to Stout?
I'm sure you do a poster, right? What did you do?
I know Point has one. I can't remember it.
Yeah, so then you can do your whole
What was that?
presentation.
I know, doesn't Point have
Good
one?
job.
And they judge
Their
it,
own
and
slogan?
they give you the award.
I don't think we did.
Yeah, so then
I think I talked to someone one time. who
last
said
year they
that,
had 4 awards,
all
2
the-
for graduate, 2 for postdoc.
like,
So that means right now they should have, yesterday they should have less than 4.
people at Madison look
People
down
who
at
are
all
signed up.
other state universities. They
No, just think
Nice.
about
For all
last
of
year.
us.
Of course.
From our group to you and Forde.
The governor
right?
said they was gonna
Yeah.
tear Madison.
Without us, there are
Yeah,
only
fine.
Be one.
All the people in Madison are like,
And
yeah,
without us,
take
how
over
many
your own
people-
people. Yes, you are. I'm kept saying it.
Holy budget.
Oh, you got one of these for appreciation?
No, Deyan is like.
the printer in physics department wasn't working.
No, I'm more willing to get.
Oh, were we supposed to print?
I couldn't
No,
figure out
he
how to
prints.
put many slides on one page.
No, mine's 6 slides.
Mine's 8, I think.
Oh, that's right.
But they're.
Oh.
Okay, we are starting computational chemistry 767. Quantum chemistry 2. It is the first time when I will sit and relax. And there will be presentations that attendees of the class were dying to make freewheel presentations, which will be counted towards credit. The subjects are covering applications of angular momentum as much as is possible and matching your research interests. The ideal presentation is supposed to be 4 minutes long, but if someone is really inclined to speak a couple of minutes longer, it is fine. We just need to finish everything by 1 when some of us need to be elsewhere. The original screen is not working, so we are fighting a little technological challenge. So you bring your slide on the computer, and then you travel a little to change the slide, and then you will see in the second screen where you are, so that both you and your slides are seen well. So if you're not sure if you're catching the camera, you can watch on the second slide. So all slides are uploaded to this computer. They are titled according to their presenter and the last name, so you can quickly find them here. And they also are brought up to the desktop. So the slides themselves cover topics from addition to angular momentum in explicit way towards nomenclature for states with high values of angular momentum, towards the complication of this nomenclature in systems where there are additional factors such as ligand field splitting. And with this, I would like to invite to the stage the first speaker, who is Deyan Mikhaylov, and he will present on connection between angular momentum addition and photovoltaics in the subject single fission. Yep, the floor is yours.
Okay, thank you for the introduction. Okay, so let's first review some Auger processes. I'm going to start a stopwatch here, just in case. So these are the 4 prevalent Auger-driven processes. Well, 3 of them are Auger, 1 of them is not, and that we see in semiconductors. Auger processes are facilitated by the Coulomb interaction. So when 2 charges interact, they interact through the Coulomb interaction. So we can have what we call impact ionization, where we have a very energetic exciton, which is an electron-hole pair interacting with the Coulomb interaction. And the highly energetic particle hits another one, for example, and gives it enough energy to excite it from the valence band into the conduction band, and that other particle also leaves the hole in the valence band. So you have, from 1 charge, you get 2 charges, which is what also referred as multiple exciton generation or carrier multiplication. And this is also an Auger process. See how the energy diagram shifts in Auger recombinations when you have 2 and so on. So, but this is the important one, multiple exciton generation. So you can have some highly energetic excitation, and you can end up with 2 singlet excitons after after the highly energetic particle excites another one, or you can have 2 triplet excitons. In either case, you need a photon with energy more than twice the gap, right, to create, to conserve energy. But what's so exciting about singlet fission is that this singlet, initially excited singlet exciton, which can only be in the singlet state, which is the reason for that has to do with quantum field theory, and it's beyond this talk, but this singlet exciton could have potentially less than twice the gap. And in that case, you cannot create 2 singlet excitons because it will violate conservation of energy. But triplet excitons, for some reason, are at lower energies than singlet excitons. And to calculate the triplet exciton energy, you have to solve your DFT equations for spin up, spin down, and all that to calculate. But it turns out triplet excitons are at lower energy, so you can have an excitation with less than twice the gap, and you have multiple excitons in your solar cell, and you have higher current at energies twice the gap. That's why singlet fission is such a hot topic for research. See some experimental results. ME and triplet, two triplets is the same thing. This is just some called multi-excital state. It has to do with the overlap of the wave functions, but that's a different topic. But anyway, so you have a singlet turns into two triplets. And here's some experimental results. How one singlet exciton with smaller energy than twice the gap turns into two triplets. And okay, so we have a singlet. We want it to be spinless. We want J to equal 0. That's the reason for that. It has to do with quantum field theory, and it's beyond this topic. But this is allowed. But you have two spin 1/2 particles, right? Electron and a hole. So according to our Klebsch-Gordon coefficients, right, these are also possible states. Turns out that this initial triplet exciton is not allowed, but it's also possible because of our addition, angular momentum addition. Okay, so, but what if we have two triplet excitons? Well, if we look at the Klebsch-Gordon coefficient table, we can see that if we have two triplet excitons, we have a case where the total spin is also 0, or what we prefer to class as J, right? Total spin could also be 0 if you have two triplet excitons. And the triplet exciton, as we saw earlier, has total spin of 1. So now we have two triplets where the spin of each is 1. But when you combine them, you get a spinless system. So spin conservation is obeyed. So what is that state? Well, total spin J, as we refer to in class, and Z component M could be 0, where we go to the Klebsch-Gordon coefficients table and we go 0, 0, and we go 1/3, 1, minus 1/3, 1, 0, 1, 0, plus 1/3, 1, -1, and 1. And this is the only possibility that the two triplets exist. And that's how you add their angular momentum. Very straightforward. Thank you very much. Any questions?
Again, for interesting presentation, perfect illustration of what you were doing in class. Any questions are welcome to the speaker. Yes. So, which classes of systems or which systems exhibit this effect? Any?
Sorry, a very popular one is pentacene. And you always chemists know what pentacene is, so I didn't bother putting a picture.
So you may ask the audience, what is pentacene?
No, I know what pentacene.
Okay, good.
What is
It
pentacene?
is 5 aromatic rings connected to each other. So
All 6-membered rings?
yes,
5 6-membered rings.
5 6-membered rings in sequence.
Why does that help these processes?
Why does pentacene
Yeah.
help? Why does pentacene have? That's
Like if you increase the number of rings, would it also increase?
they don't see that in other polycenes. Pentacene is the most efficient one for singlet to two triplet conversion. This transition where you have a low energy initial excitation to two triplets is very efficient in pentacene. That's why it happens in other polycenes, but it's not as efficient.
Is it due to like the quantum confinement of the ortho box, like the size of the box?
Or why that is an efficient process is a debate out there. No one knows why. No one really knows. Well, no, confinement enhances the Coulomb interaction. So confinement enhances this effect.
So you want to tell that
But there are
confinement acts
other-
differently on singlets and triplets?
Confinement has, well, the Coulomb interaction doesn't facilitate spin. You have spinless system, Coulomb interaction, spinless system. Why the two triplets are at such low energies in certain materials is a very difficult question. There are other confined systems where this is not strong. This is not very favorable reaction at all. Or maybe it is, but the triplets are about at the same energy as the singlets, and then you don't gain much. But
Good. Let's thank Deyan for bringing up the challenges of the modern science to the class. And with this, I would like to invite the next speaker, who is Samuel Brown. He will continue illustrating subject of angular momentum, and he will continue to bring in challenges of modern science to our classes. As you can see from the front title of the slide, nitrogen plus vacancy defect in diamond.
So this is my presentation, and I don't work with this very much, so I'll kind of use that as my initial cop-out, I guess. So this is pretty new to me, so I'm not going to be nearly as competent as Dan was on his last one, but I always like to start with a nice joke, and this is kind of how I sometimes feel with this presentation. So, here we are. Can everyone read this? So, just great to start off the presentation. So nitrogen vacancy. So just, I guess my initial question was, what is nitrogen vacancy? So it's within diamonds that you'll usually have it, and instead of one of the carbons, they'll have a nitrogen and then a vacancy, so nothing there. So then you have like a free electron with its spin, and then one of the carbon atoms with its spin. That's what they use to probe this quantum state. I think one of the most interesting things from me being an experimentalist is that they can probe this at room temperature and using optical means. So I know I work with optical means, and it's something I think a lot of the other quantum states or systems that they're trying to work with require really, really low temperatures and stuff like that. So again, it's just interesting. This is a group I think out of MIT, and they use a confocal microscope setup to deal with it. So this is just a picture from their website. And then, so diamond, we've all seen a diamond that doesn't typically fluoresce or have anything like that. But when you have a nitrogen vacancy, that will bring the band gap within optical ranges. So here is the typical band gap of, or this is the band gap of one of those nitrogen vacancies. And then they were fluorescing this with 532 nanometer emission sight or laser. And they're getting this red fluorescence throughout. This is a confocal image. So kind of cool just to see that. And then I'm a little rusty and I wasn't able to have the time to fully figure this out, but they're able to split the states from the ground state and excited state into these three different spins using magnetic fields. And with these magnetic fields, they're able to then isolate two of these states from the other one, so that they only have one state that they're actually dealing with, and that's how they're able to get look at the spins within that system. And it had to do with this state here, which I can't exactly remember or couldn't find what that was. But recombination through two of the spins would go through that state, where only one would come back through radiative transitions. So then this is just a little thing on quantum computing. This is so I think they use like ion implantation to inject the nitrogen source into the carbon lattice, and they're hoping to get more and more nodes. You can actually have like a quantum computer, and this is just work trying to deal with that. And then there's this commercial thing called a D-Wave, which is an actual quantum computer. It doesn't use this technology, but it's owned by Google and NASA. You kind of need it, so. Questions?
Oh, some for interesting and for matching the schedule, ideally.
Dan went a little over, so I thought I'd try to jump on
Thank you.
it.
Thank you for
I'm
cooperating.
here for you guys.
So, questions to the speaker.
I have a question about the diagram, on the diagram slide. Yep. So could that A1 state be the bottom of the conduction band, and just this GS and ES is just some ground state to some arbitrary excited state, and A1 is like the bottom of the conduction band, which is like a long-lived state, so that that's where those split excited states just relax to.
You're saying this is the
So-
bottom of the.
Well, this A1 is some reference state, right? So that all excitations seem to go through.
Yeah, and when they're saying all excitations, they said only two of the spins, so the 0 and or negative
Oh,
0
okay.
and +1. So that's why they were saying they're able to isolate one spin, and that was the interesting thing. Just the one spin was the one giving off the fluorescence.
Oh,
they
so-
did ideally keep that. So I'm pretty rudimentary on this, so I'm giving you the best I
Yeah.
read from the little bit I did.
So, how is this system open shell? Because on slide 2 you show a diagram of it, and the vacancy is where the nitrogen has 2 lone pairs. So, does the
think
open shell come from the 3 carbons around it? Like if you look at the vacancy, the 3 carbons would have 3 different electrons. Is that where the vacancy is coming, or is it from the nitrogen?
The vacancy as in.
I mean, the unpaired spin.
I think it comes from one electron being here, so you have one electron. I think one stays next to the nitrogen. I'm not sure. Then you have a carbon-13 atom, so one of the carbons is also
Carbon third.
looks like a nuclear spin or something. And I can't remember.
So it is not because of the nitrogen has odd number of electrons. Just throw in hypothesis.
I remember.
You'll
just-
erase the records if something like that.
I thought they were saying there's like the two of the spins, like maybe this was 2 different things I putting together. But there's like a nuclear spin and a quantum spin. So I thought like, there's one that was a carbon-13 that they were referencing.
Oh, so you have to have a nitrogen and a carbon 13
I think
within.
so, but I'm not exactly
Whoa.
sure. I try to get a little bit more, and I just didn't have the time to find more on how this is actually made. But the little bit I thought there was a carbon-13 that was involved as well. So.
Okay. More questions? Let's go forward to the next slide. And next one. So you've mentioned in your Dibler's figures about quantum computing being absolute progress and nothing started in the superposition. You saw his edit. So for quantum computing, you need 2 states. Which you're showing like 7. Which of those will form a qubit to build a quantum computer? Just hypothesis.
Yeah, no, so that's what I was, and like I said, I think these 2 go through this state. So, I think it has to be this one and this one, the N0 state, because these ones don't recombine, so you stay in MS equals.
So you have hypothesized that it is 2 states separated by optical energy offset. Okay. If you want to store more than 1 bit or more than 1 qubit, then you have several of those.
Yeah, so I mean, I think that was more what they were trying to do with this stuff. They were trying to get more next to each other and have entanglement and
How the
stuff like that.
excitation transfers from one to another one through which mechanism? Just hypothesize.
I mean, tunneling or something like that.
Or maybe Forster or Just
I think it depends on the system that they're trying to work with. Like sometimes they want to have like an electric field next.
channeling in diamond, in dielectric.
Like, are you saying you want more than one?
Diamond is dielectric. Yeah, it's not perfect for diamond.
I was thinking like, so they don't always use diamond, I guess, and I think they use diamond for the majority of their stuff. But I think some other guys are trying to use silicon where they want to have stuff closer to each other. I think that's like another research that they're trying to work on, is trying to get them close enough to interact.
Okay, okay. More questions from the audience? If no, let's thank Sam for bringing up this interesting topic and inspiring us to look on it deeper. So, who is the next?
And then, yeah.
Next presenter is Brendan Gifford, and he will present on the nomenclature for states with high value of angular momentum, spin momentum, total momentum in practical application to lower rows of periodic table.
Okay, so I'll be talking about the term symbols for the lanthanides in the +3 oxidation state. And so if you want to know what the lanthanides are, they're these ones, in case you don't remember from general chemistry. So we're going to talk about those 7 in the ground state and the excited states with both spins, or both the spin flip and no spin flip. And so here's the equation we're going to use. You're all familiar with it. Here S is going to be the spin. The L is the total angular momentum from the orbitals. And J is the total momentum when you sum those two.
What? Angular? Total angular moment?
Talking about L.
So, J, you said total momentum?
Total momentum summing the angular momentum and the spin.
Okay.
He was, Deyan was highlighting that it is angular momentum
Oh, angular momentum.
associated with rotation rather than
I see.
linear velocity.
Gotcha. Oh, yes. Okay, so the first one we'll look at is lanthanum, and I apologize because this is the only one that I can actually pronounce. And so with lanthanum in the 3+, charge of 3+, we think first in general you're going to have 3 orbitals in the 4f orbital. Again, that's not necessarily true, but we're going to go ahead and assume that they're there. And so they may be in some lower or spread out throughout d orbitals as well. But so we're going to take those 3 out to get to the 3+. And so we have no electrons in the valence shell now. So L, or so for all of the orbitals in the 4f level, they're empty. And so if we apply our cool little equation, we can see that S equals 0. There are no spins in it, so it's a singlet. L equals 0, so when it's 0, we call it S. And then J equals 0 plus 0, which is, or 0 plus or minus 0, I should say, which is 0 or 0. So we're going to say it's 0. And so the result is going to be 1s0. Okay? And so then if we go to the next one, which is not going to come until I click again, cerium. So cerium has 1 electron in the valence shell in the same model as before. And so if we apply our equation, we see we have 1 spin, so it's 1/2. So 2s plus 1 equals 2 is doublet. L equals 3 because we're summing across all of the orbitals. And so there's only an electron in 3, so it's 3. And so then it's 3 plus or minus 1/2 for the total angular momentum. And so we're going to choose the lower level, or the lower value according to Hund's rule in the ground state. So we're going to choose 5/2. So the result is going to be 2f 5/2. All right, and then if we look at PR, so PR is anyone know how to pronounce that for me? You want to help me out? No? Praseodymium? Praseodymium? Okay, so if we look at praseodymium, dymium, I don't know. It's applying the same formula as we did before. Now we have two spins, so it's going to be a total spin of 1, because you add 1/2 and 1/2. You get 1 triplet, L equals 5, because you have 3 plus 2. Now you have electron in the 3 and the 2. orbital. And so now J equals 6 or 4. So Hund's rule, we're going to choose 4. And so we get 3H4. All right, and so we'll very quickly do neodymium. Neodymium? What? Neodymium in the same way. So we're going to apply the same thing, concept we had before, and we get 4I9/2. So the same is going to apply for our promethium. And so you start to see a pattern. All we're really doing is we're adding 1 up here. And so L is still going to change. At this point, we didn't add anything. We added 0. And so, so then J is still going to be the same. And so we have 5I4 for samarium. Same rules. We have 6H5/2. And then for the last one, europium 3+, we get 7F0. Right, okay, so those are all in the ground state, and also we know that those were also in the book, so there was definitely a key, and so I can guarantee that all those are correct. So going forward, we're going to look at excitations. And you know how some people wake up in the middle of the night with an aha moment, they recognize that, or they're able to solve a problem which they were previously unable to solve. I'm the reverse of that. I wake up in the middle of the night recognizing what I had done wrong in the previous day. So last night at about 4 a.m. I woke up and I said, aha! In L equals 3, I forgot to consider, so in the spins here, I considered the spin in the lower level shell, or the lower shell, which is not full now, but I forgot to include that in angular momentum. So I may have made an error on these slides. I guess we talk about that. On this slide specifically. So this one is a little tough because we had to think about the electron from coming from, instead of the 4F orbital, we had to think about it coming from the next lowest shell. And so to my understanding, the next lowest shell is actually going to be the 3p orbitals, or no, 4p, right? 4p orbitals. And so the next lowest in energy. So we have to think of the xenon shell, the 4p orbital, one of those electrons coming from that, right? So if we were to excite with spin up from that shell, and then we're going to leave the spin down electron in the previous shell, so it'd actually be, can I write on the board? Or, okay. So then the 4p is going to be, oh, it's okay, they don't need to see that. They'll be okay. All right, so here's what we have left over in the 4p. So we have 1 downspin in the L equals -1. All right, with me? Okay, so in this case then, so the 4p, right below this, we still have that 1 downspin. So if we were to take that 1 unpaired downspin and add the 1 now unpaired upspin, we get 0. So we still have S equals 0. Everything's all the spins are canceled out. So we're going to call it singlet. Here's where I think I made the error. L equals 3. I was thinking there's 1 in the 3, but we also have to look at the total over there. We're going to still have 1 left in L equals 1, right? Because there's 1 more in L equals 1 than -1. So we should get another 1 from that orbital. So we should have L equals 4. So instead of calling it F, we'll call it A, B, C, D, E, F, G. Okay, so it'll be G, and so this actually should be 0G, and then here we're choosing 5/2 for the spin conserved. And then for the spin flipped, where we have the spin match, we have the same L, because it's still in the L equals 3. We still have the situation over there. We have now S equals 1 because we have the spins are matched, and so this one then should be 3G, and now we're choosing the higher level for the J because it's a spin flip. So we'll choose 4. So we should get not these answers. 1, it should be G 7/2, and 3G 4. I think that's how you deal with those. Okay, so cerium now it's a little more clear cut. We can consider the xenon shell totally full, or just the valence shell in the xenon totally full. And so now we're just taking this 1 electron and we're moving it up one orbital or flipping it, put it in the same orbital. And so applying the same math which we had previously for the ground state cases, we get 2d3 halves and 2 f7 halves. And so this is going to be a little boring, but going through, we're going to do the same thing for the next one. And so for the spin conserved situation, we get 3g3, and for spin flip, 1i6. I don't think there was anything weird here that we had to think about. So spin conserved for neodymium, 4h7 halves, and spin flips to k17 halves. And then for promethium, 5h3 and 3l19 halves. And then for the spin conserved for samarium, 6g3 halves, and then here's where you really have to start counting up the alphabet. For this, L equals 11, so it'll be 3n 9 halves. You get some weird looks.
Why did you flip 2 spins?
Did I flip 2 spins? Oh, you're right, I did flip 2 spins. You're correct, I flipped that one and that one. Why did I do that? I copied and pasted the wrong one, I guess. Oops. So that one's not correct then. So that was painless, right?
Almost.
Almost painless.
The
Good thing,
numbers
Brendan.
is right. The
Questions.
oh, on that
The numbers
last
were
one, the number is right because you get 6, 4, 5.
I should get
Oh, wait, no.
2, 1, 0, 2 3s, right?
Yes.
Yeah.
So yeah.
So I should get 3, 4, 5, 6.
But I do have a different question. For lanthanum, when you do a spin flip, is that actually just a spin flip excitation?
For lanthanum,
Yes.
this one only spin flipped excitation?
Yeah, is it a pure spin flip? Or is there more stuff going on than that?
Well, this one I'm exciting from the lower level and doing a spin flip. So I assume you're saying no?
I'm asking.
The answer is no, because I've taken it from the lower energy, the lower shell as well. So I guess I've taken it from the lower shell and in the spin flip. But I guess in all of these, I'm not thinking. In all of these, we're also doing the same thing.
More questions?
Why is the spin up in the spin conserved system? Why can't you just take a spin down from the lower end?
Well, if we took a spin down, we get the same thing, right? Because we instead of so S would still be 0 because then we would be adding the leftover up and down to get 0, and then L would still be 3 because it would still be 3. So I think we get the same thing if we excited just a spin down instead of spin up. Oh, sorry, question.
No, it's fine. Wouldn't you have to consider the L from the lower shell too as well, since that would have some sort of contribution?
Yes, yeah, and that's what. So I'm going to, or so yeah. So that's where the 3 is incorrect. I should have added the 1 as well, because I believe the 4p orbital is the next lowest energy. So yeah, I should have added that one.
So is it 3 plus 1 or 3 plus negative 1?
Well, I'm looking at the contribution over there is you take 2 times 1 plus 0 times, or plus 2 times 0 plus 1 times negative 1. So you're adding 1. And
So
the
you're not
contribution-
just adding the empty spin from the bottom orbital, you're adding everything from the bottom orbital.
Yes, because normally you would be, normally if you did that, you'd get 0, right? Because the shell below the valence shell is full. And so,
Right, but when you have an excitation.
but when I took it from that orbital, I assume I'm supposed to add that.
Is that right?
Hmm?
Is that right?
It is reasonable.
I have another question.
Javid was first.
It's not a question actually, I don't know, that's why I just want to know. When you make a lanthanum 3 plus cation, So when this other two, sorry, I mean rest one, this electron is releasing from 4f. Why not from the 5p?
Why not the 5p? Well, there are no 5p orbitals in this one.
Previous one is a 5p, right? 5p, 6, then
No,
4f,
5P is
1.
on the same.
Okay, so for these, I essentially said that they're all coming from the 4f. That's an approximation because if you look at the lanthanides, they really, in reality, they distribute them between the D's and the F's. So I've just
What is the
considered-
previous orbital
Yeah,
of
orbital.
4f? Is a 5p, right?
Yeah, it's
Xenon,
5P.
yeah. I mean last orbital of
Yeah.
So you're saying I'm taking them from the 5p and not the 4p? Oh, thank you.
yeah. I mean I don't know why I'm.
Oh, okay.
But that doesn't affect it, right?
No,
No, I'm not
still
talking about
the
spin. I'm
momentum.
talking about why when you make a 3 plus cation. So why this electron doesn't come in from the 5p? Why is
So if I were to have lanthanum,
yeah?
just elemental lanthanum, I have 3
Yeah.
electrons in the 4f. Again, I'm approximation, but so when I took out those 3, I said this is higher in energy than the p orbital below it.
No,
so I
we-
removed
Let
those 3.
me translate the question of Javid. He's asking to open the off-bow principle for xenon. He's interested what is inside the square brackets. What if
Yeah, it's not
last
only
record-
it's not only xenon. I guess it's 6s2 4f1. Am I right? I don't know.
6s2.
Is it like regular ascending
Outbow
trend, or
principle?
there is some flips?
There might be some flips in there.
I think you take 2
Yeah, I-
minus the last P to get the F. So then you add 2, so then that would be 5.
So what you're saying is the 6s or the s right before this, right? These s or these s here, right?
Yeah, 2s.
So those s are those higher or lower in energy than these f's? I'm sorry, these f's.
No, look at where xenon is.
Xenon, yes.
Yeah.
What level? 4P or 5P is that row on? That's what he's asking. That's
It's a 5p6.
I think the highest energy electrons from the xenon shell are
5p6.
sure,
so
Yeah.
then,
not 4p, 5p.
No. Then
I think. Well, yeah. Actually, I think in those little letters is our answer, but I can't read them. Oh no, never mind. That's the mass.
yeah, then 5p2. I guess.
but
Okay.
it doesn't change L.
No, I'm not talking about this one.
So
I'm
let's-
talking about to make. Yeah. Okay, I can talk it later then.
Okay.
Okay, let's thank Brandon and all audience for supporting this vivid discussion. And the next presenter is by Aaron Forde, if he doesn't mind to present. And he wanted to tell something about what if the spin and orbital angular momentum are not good quantum numbers anymore. At least some introductory discussion of the subject in application to new material lead halide perovskite.
So, hi everyone, as the title says, I'm Aaron Forde. I was going to talk about spin orbit coupling and lead halide perovskite materials. So lead halide perovskites, so the perovskite is the crystal structure, which is shown on the bottom right. And then the lead atoms occupy the corner spots of the crystal, and the iodines coordinate octahedrally. And then you can have some sort of charge stabilizing cation in the middle. And these crystal structures have useful properties for next generation electronics, for either for solar cells or topological electronics and all sorts of crazy stuff. So for this presentation, I'll focus specifically on cesium lead iodide perovskite. So the electronic structure of these crystals is the conduction band is primarily made up of hybridized 5p orbitals. Sorry. I have that back. The valence band is 5p orbitals, and the conduction band is the 6p lead orbitals. And then these atoms are heavy enough where spin-orbit coupling interactions will have the potential to split energy bands in these systems. So those will have to be considered, and that's what I'm going to talk about. And I guess I forgot to mention, and all these are just stabilized by charge, so they're all actually closed shell in the ground state, where lead is 2+ and the cesium iodine are 1-. So for doing these notations, it would be kind of, I don't know, it wouldn't be very exciting to do these notations for closed shell, so I just did it for lead just to show that I can actually do it. So for the ground state, just regular lead, you would have 3p0 because 2 spins would give you a doublet, so those add to 1. So you get 3, 0. And then if we excite it, you would have still spin 1, but then you would increase your L to 2, so SPD, so that D would be your letter, still have a triplet, and then you'd have a 1 for your total angular momentum. And the little spin flip would be just flipping the other spin, so you get net spin is 0, so you still have a high angular momentum of 2, so you get 1d2. So it's a singlet instead of a triplet. And I did have some more to put on this, but I missed the midnight deadline that was imposed on how to calculate these. But this is just from a paper explaining I did some computational studies on the spin-orbit coupling splitting of the band structure. So you can see these orbitals up here, those are from the lead. And the left side is before spin-orbit coupling was introduced, and the right side shows the splitting. So you can see this band here goes up, drops all the way down by almost an EV, and then these two bands up here, they split upwards by about half an EV. And then the iodine valence bands, they stay relatively the same. And then if you do some calculations from perturbation theory, like they roughly match about what is shown in here. So for the split down, the calculation is about 1 EV, so as you can see, that's about roughly correct from the calculation from perturbation theory, and the spin upwards about a half EV, which I was going to show, but I missed the deadline for that. So yeah, that's all I had to show.
Okay, let's thank everyone. And everyone is welcome to give him a pleasant time by trying to answer what was missed, what he was planning to add to the presentation. Questions?
Yes, I.
Please.
So on slide 4, the next one, fast one, for the middle one, you have -1 and 1, but you say that L is equal to 2. Is that correct? And can you please explain?
Yeah, is it just you add the magnitudes of the orbitals numbers? So if these are our ML states, then we just add the magnitudes of the numbers?
No. That's only for the split.
Take into account its projections. It's vector summation. So it is a z projection, and you take into account the same.
So should L be 0?
Yes. Should be 0.
And then for the next one down, should L also be 0?
Yep.
Okay. So then what
Good
would
catch.
be the letter for the middle one?
So if L is 0, it would just be S, right?
What?
Yeah, looks like this.
The ground states. Well, you just have the arrows different. One and
No,
0.
it should be a positive going
Yes.
downward, but
So can you go to experimental computer? Yeah. So you have splitting of about 1 EV for lead, for the band localized on lead ions. So what is the criterion for an arbitrary ion in the crystal forms of arbitrary ions? When the spin orbit splitting is higher, when it is lower? Which criteria contribute to the value of spin orbit? Like, is there a spin orbit coupling for states with lower angular momentum and low spin? Just speculate.
So for like lower weight atoms, you
Speculate on which factors affect the spin orbit splitting.
So it's proportional to like the atomic number, and it's inversely proportional to like the principal number. So the further away you are, the less splitting you'll get, and then the higher weight of the atom, you'll get more splitting. And then the splitting is dependent on the fourth power of the atomic mass. So the heavier you get, the more pronounced splitting you get. Which is why it shows up for lead, like pretty pronounced. So you get about an EV of splitting to reduce the band gap.
Any other factors?
Those are the two terms from the equation that.
Does it depend on the value of orbital angular momentum and spin angular momentum?
Yeah, depending. So the difference. So if you do the maximum J state, that will. Well, it's either or. So the maximum J state, I think, takes the lower value. If you're in a lower angular momentum state, that shifts the states higher. So your lowest angular momentum state will be in the bottom, one, and the higher ones are the top conduction bands, or higher up in the conduction band.
More questions to the speaker? More questions 1? More questions 2? More questions 3? Let's thank Aaron. And we have 2 more presentations, which will cover next area of interest. So by now we were speaking about the we were speaking about systems where angular momentum itself plays a major role, but in some systems there are additional factors. The influence of neighboring ligands may also affect which states with which momentum will take the lowest energy. And Javed Mohammed will tell the role of angular momentum in states of dilute magnetic impurities in quantum dots.
Thank you. Maybe I couldn't able to explain everything what he said, but I will try to explain the spin orbit of this manganese in the quantum dots. So this is just a review for this. What the term symbol, I guess, is already known everyone. So this explaining 3 term here. And now I'm considering the cadmium solenoid quantum dots. In cadmium solenoid, if we first see the spin of the cadmium solenoids, they have a spin of 0, total spin in case of 0 always, and this is a term symbol for cadmium solenoid 2 minus, and this one is for 2 plus, and it's always 0. If we get the undoped cadmium solenoid, total spin should be the 0 in this case. But if we consider the manganese, this one is the manganese 2 plus, electron occupancy in the 5 degenerate d orbitals, and calculated the term symbol for this one is 6s52. Already shows how did I calculate this one too. And but this one they have some splitting in the depends on the what's the bond type. If from the octahedral, the splitting between these two are much higher. So that's why this 2. It's they have a difference than Ohm's rule. It all occupies these 2 dxy and dyz, and it's showing only one single spin, up spin in the dyz. But in the tetrahedral cases, in the pure tetrahedral cases, the splitting energy between these 2 are very small. So that's why electron can be occupied according to the Ohm's law, so is the form a high spin system. But in case of when we dope the manganese ion in the cadmium solenoid, it's not a pure tetrahedral. So in this case, it can be for distort from the pure tetrahedral shape. So before that, as the question says, I'm trying to show the lowest spin ground state. In this one, I consider this one because it's showing the spin is lowest. When we excited these sp electrons from the excited state in the excited spin, and then the terms is going to the 2h9/2. And in case of lowest spin flip excitations, they have some confusion to me. That's why I consider these two. In these cases, this one electron and the one pair electron is excited to the empty orbital. In other cases, I just flip this electron spin to the plus half to negative half. If we calculate the term symbol for this one is going to the 4G, and this in this case is with 2I13/2. It's just opposite spin of this in the ground state. And after, by the effect of the ligands or cadmium on the manganese, this can be further splitting. So it's showing us the 3 splitting. I don't understand this figure, so I just try to explain what I said. In case of 0, it's kind of 0 energy to be split. 0 splitting is showing the 4G, and 6 as this one is a ground state. And but after the increasing is the 4T1, this is the lowest excited state, and this is 6 as this one is still the ground state, showing into the ground state. And it's if we see the previous slide is showing that is a higher spin state. So, and this one, so high excited state of this manganese in this entire excited state is higher spin, and the ground state is a lowest spin state. Yes, this explains this spin state of this quantum solenoid things. And if
Okay,
you have any
let's thank Gifford. Presentation is open for discussion.
Can you go 2 slides back? So, question, your bottom 2.
Yeah.
What would be the limiting cases for them? So, how would you get the second from the bottom, and how would you get the bottom?
And this one?
Yeah, how would...
This one is just flipping this one.
No, due to tetrahedral splitting.
Due to tetrahedral, what I showed in this case from the tetrahedrals here. In this case, can be this electron can be flipped down.
So, if your splitting is bigger, what's going to happen?
Oh, in this bigger, then it will be happen like this way, and this electron will be.
But that's octahedral, we're still in tetrahedral. Right, the top ones are going to drop. So, for the 2 on the bottom, on the next slide, what regime are you going to be in? High spin or low spin?
From the bottom, in the tetrahedral case.
On the next slide, you have the 2 spin flip excitation.
Yeah.
Which one relates to low spin and which one relates to high spin?
This one is just to the low spin, because this one still is the lowest spin. So if I compare with this one, then just only spin is flipping is giving us this one.
So then the top one is?
Top one is higher than this spin. It's splitting much more than this one.
There is a reason. There is very important aspect to discuss between all of us related to transition metals, where orbitals experience splitting. Before, so all speakers before Jabet and all materials that we covered in the course were relying on the magnetic quantum number, M sub L, projection of orbital angular momentum onto the axis that takes positive and negative values, they are discrete, -1, 0, +1, -2, -1, 0, so forth. On one hand. On another hand, here Jabet comes and starts using notation dxy, dz square, dx square minus y square. would it be correct to tell that such symbol would correspond to a specific value of the magnetic quantum number, or the situation is more complicated? What is the correlation with this geometrical symbols, dx squared minus y squared, and values of magnetic quantum number? What is your opinion?
In these cases, it's oriented. These two, I mean, z squared and x squared, y squared, these two are, I guess, oriented in the. I can show the graphically, maybe that would be the easier way. If these form a tetrahedral shape like this one, in case of last two, z squared and x squared minus y squared is form a. Can be perfectly, it was from here. And other three, this d orbital will be in this axis, I guess.
So you are making an argument about better overlap with ligands.
Ligands, yeah.
Okay, but what about quantum numbers? M sub L. Yes or no? Or maybe? Of course, is there a one-to-one
Yes.
correspondence between these
Yes,
pictures and
In this case, xy, yz, and zy is negative 1. I mean, -3, -2. So -2, -1, 0.
Does it depend on the energy of them, though? Which one you label?
It depends on the octahedral shape. It's change their energy, splitting energy is all opposite in the octahedral and shape. I guess I showed in the last previous one. Oh, yeah. So in case of octahedral, these are in the lower energy than these two orbitals. But in tetrahedral, they flip down. These are higher than these two.
Okay, it is an inspiration to continue the discussion. Please keep thinking of it. It is not it is not most complicated question, but we need to work on it more and at least have the answer by the end of the course. More questions to Jabet? If no, then thank you once again. And we do have last presentation in today's program by Levi Lystrom, who will continue the same subject of matching between angular momentum and ligand field splitting on the example of metal-organic complexes.
Thank you. Thank you, Dimitri. So, as Dimitri said, I'm going to talk about tris by pyridine ruthenium in two different oxidation states, 2+ and 3+. So, first, let's figure out the field that the ligand's going to give. So, if we look at the spectrochemical series, bipyridine is very high up it. So we are going to have we're going to be in the regime of low spin. So that means if we have electrons that are more than 3, we're going to start pairing them instead of having them go to the upper one. And since this is a octahedral, we'll do octahedral splitting. So this is the two cases. So with D5, that's when we have the oxidation state of 3+. So we have two states that are fully occupied and one that is singly occupied. And then when we do D6, which corresponds to 2+, all 3 of the lower ones are occupied. So this is the complex we're looking at. When we get to Russell-Saunders terms, they get much more complicated because the S and the P terms, they are comprised of a single kind of like symmetry, but as you increase the angular momentum, they start to break down and you have like linear combinations. So if we look at just a simple example of a tetrahedral, and in his T2G, and there's 2 electrons in his T2G, which are the lower one, and EG is the higher one. So this configuration corresponds to 3T1G, which is the symbol that replaces the like S and P when we have ligand field theory. And like if we do different excitations, we can have like 3T2G or 3A2G, which I believe in Sam's presentation when they had the intermediate step, they were referring to these CHEM symbols, which had a specific combination of electrons, but I'm not 100% sure since I did not look at the paper. So we will go from the alphabet to these guys, and in this we will look at very similar diagrams that Gifford brought, and I'm not going to try and explain announce the name, but for the oxidation state 2+, we look at the D6 diagram for octahedral, and we see that once we go from the spherical and we go include our ligand, we will have a very dramatic change, and we can automatically assign our ground state in the regime of high spin and low spin. And since our ligand is a low spin complex, it will lie beneath 20 to 50, somewhere in this region. So we can assign all sorts of states just by knowing what terms mean. However, I didn't go through and figure out all of them. But our ground state will be a 1A, 1G, which I have no idea what any of that means, but that's the ground state. So if we go to oxidation state 3, you can see that the diagram dramatically changes, and this is the diagram that Gifford had in his presentation. And we should be somewhere in the the low spin regime, and we see that our ground state goes from a 1A, 1G to a 2T, 2G, which I kind of wish I knew what those meant. But if we go back a slide, it probably has something to do with it has 2 electrons in the T2G and none in the E. So these diagrams are very helpful, but I didn't go and figure out the one. So the conclusion is, since we're in the high regime, low spin regime, our 2 ground states are 5T2G and 6A1G for the ruthenium 2+ and the ruthenium 3+ respectively. And I would like to open it up.
Okay, let's thank Levi. So now we are not limited by necessity to give space to other presenters, only by our wish to go to the bench. So any questions to the speakers?
Oh wait, we're not limited in time?
Oh,
You can give him hard time.
Well, I just have a difficult question potentially. Why did you switch to this TA2G, 1G? What does it mean? Like, what-
because the ligand field breaks symmetry. So if you actually write down all of the exact energy of these guys, they're not degenerate anymore. Like they very smallly change in energies. So you can't use, when you do the SPDF and all those, it is more for when the energies are almost like exactly degenerate, but when we introduce the ligand field, the magnetic field, and all of the electron coupling, break that symmetry dramatically enough to break the fact that these are supposed to be very symmetric. So then we have to go to ligand field theory like values, because if you look at ligand field theory, all of the symmetry of the orbitals, all of them are lowercase. So these are actually the terms, like ligand, these are the terms that you can get from the I's, or H or G or F, P. So since we're introducing a large perturbation, we can't stay within the degenerate.
So you're saying when the orbitals within a certain, or with a certain angular momentum are no longer degenerate, you have to switch to this other system.
Yes.
Okay.
Satisfied?
Yeah, I think so.
Questions? Can you teach us a little?
Oh boy.
So you take orbitals and out of them you compose terms.
Yes.
So here you have this lowercase t, e, and the powers.
Yeah.
T to the power 2, e to the power 0, t to the power 1, e to the power 1. How do you read? What do this notation mean?
I don't know.
Try to guess.
So I would say you can probably have a triplet out of this. No? Like the electrons.
So
I don't.
this group of three orbitals, which orbital symmetry symbol do they correspond to?
Yeah, the
Okay.
G2G,
Okay, and this group?
the EG.
Okay, and what does number 2 and number 0 mean?
So that means that there's 2 electrons in the lower one, 0 in the upper.
Yes, and here,
There's 1 in each.
so it is just algebraic notation of your energy diagram.
Yes.
Good. Everyone is happy with this? Okay, more questions?
Oh, so you didn't want me to explain these? Oh, okay. I thought you were saying
too
you
com-
have this. How do you get to that? I was
no,
like,
Too complicated.
Can you explain the ones on the bottom? Just kidding.
no, I can't.
We're going over those next week, though, right?
No, done with
Oh.
No,
go,
like-
go to simple
I
perturbation theory.
I talked to someone about this, and this to understand all of this would be like a semester of inorganic,
Well,
or a good chunk of it.
there is a connection between perturbation theory and this Wiggin splitting, but I'm not sure if you have time to cover it. But I still have a question. The same as to Gifford. Can you go to the next slide? And one more. Good, here. So can you guess what I'm going to ask?
What values of L these ML these were?
Yes.
So I would think it would be 2, 1, 0, -1, -2.
How sure are you, or you have some doubts?
I have doubts.
Good.
This is just
Good that you have doubts. Let me put you on hold button and ask what Deyan thinks about it. You know d orbitals? Eigenvalues of total angular momentum. And if one writes it in Cartesian projections, well, not Cartesian, in spherical coordinates, there will be two independent operators. One depends on azimuthal, another on the like,
Theta and
theta, yeah. And the M sub L corresponds to dependent on the phi angle.
so then if
Is it
was
like
within-
-101, -2 + 2?
Let me invite you to a little journey in the imaginary space. If you have operator of angular momentum projection in spherical coordinates, it will look like d over d phi. The dependence on angular momentum will have the form of e to the power I phi times m sub l, right? No objections. So if you have discrete real quantum numbers, then the wave function corresponding to angular motion is real or imaginary? Imaginary. Okay, and here your functions, are they real or imaginary? Yes. So these functions are superpositions of true eigenfunctions of the azimuthal angular momentum. Therefore, they do not correspond to fixed quantum number. So there is no one-to-one, well, there is a correspondence, but it is not one-to-one. So one cannot assign and tell exact numbers except only one of them that corresponds to m sub l equals 0, which is, I think so, yes.
I mean, that's the one that has.
Right. Others are superpositions. Make sense? Make sense to everyone? Let's discuss it again when we meet for longer time.
And
Because-
write stuff down because it's much easier to understand when you see it than when you hear it. Any other questions?
See, he has energy to answer
No,
the
I
questions.
really just want to get off camera. So if people are just sitting there like,
Entertain us.
I did.
Okay, let's thank Levi once again. Many thanks for your enthusiastic energy, for completing and submitting your reports prior to coming to the stage. This is very well appreciated. The meeting went very organized, and I'm so happy that we touched this hard area. I believe that the rest of the courses will be easier and more intuitive. With this, meeting number 7 is dismissed. See you on Thursday for the perturbation theory. We are going off record, but I will stay here to answer questions if any.